Okay, so polynomials. Quick introduction. This is really not a big deal. Important class of function. Polynomials. Why is it doing that? It's not supposed to do that. Okay, polynomial function is a function that has this form. Now this looks really complicated, but this is something you got to get used to a little bit in math. Thinking of stuff, writing stuff in a general form. What does this mean? It's a sum. Notice that if you look at this thing up here, it's just a sum of terms. I've got this term, a sub n times x to the n, plus a sub n minus 1, x to the n minus 1, plus, what do these three dots mean right here? Yeah, what's that mean?
It just keeps going.
Yeah, it just means kind of et cetera, et cetera. Follow that pattern all the way down until you get till you run out of terms. Till you get down to, you started at the nth term, and n could be whatever. It might be 10, it might be a billion, who knows? But then you get down, finally, you get down to a sub 1. You've walked all the way down from 10 to 9 to 8 to 7, etc., down to 1. And so when n is 1, we call that coefficient a sub 1 times x to the 1, which is just x. And then finally, when n is 0, the last term, the 0th term, we'd have a sub 0 times x to the 0. But what is x to the 0? 1. Okay? So that's a polynomial. Now, what do all those a's mean and n's mean and stuff like that? They're just numbers. So in real life, this is going to look like, for example, a polynomial would be f of x equals negative 3x to the 4th plus 2x squared minus x plus 11, something like that, right? It's just a sum of a bunch of terms that all consist of the same thing. A coefficient times a power of x, and that's it, okay? This looks kind of complicated maybe, but that's really all this is saying, is you're going to pick some value of n that's an integer, that's a whole number, and whatever n is, that's going to determine how long this string of terms is, right? If n is 4, then we could have a total of n plus 1, or 5 terms. We'd have an x to the 4th term, an x cubed term, which in this case isn't there because it must be multiplied by 0, right? The coefficient is 0, plus an x squared term, plus an x to the 1 term, plus a constant, right? Okay, so the characteristics then of a polynomial are just this. It's a polynomial when you add up all these terms. The coefficients, we call this, these are all the coefficients of x. The first one, when we write this in its proper form, which we'll talk about, is called the leading coefficient. Okay? We call the last term that's multiplied by x to the 0, so it's just a, multiplied by 1, so it's just a number by itself. We call that the constant. And we say that n, which corresponds to the biggest power of x, is called the degree of the polynomial. Okay? It's in standard form if we write all of the exponents in descending order. Okay, now where's the thing I'm looking for here? This is kind of a, I don't know, this PowerPoint's a little bit strange, but the other thing, maybe this is on the next slide, but just in case it's not, each of these terms that we've talked about, these are the characteristics of the two parts of each term. Each term consists of a coefficient and a power of x. The powers of x have to be whole numbers. All the exponents are whole numbers. Can't be negative, can't be fractions, can't be decimals, can't be irrational. They're simple. They're just whole numbers. 0, 1, 2, 3, 4, 5, etc., up to the biggest power. Now the coefficients, anything goes except imaginary numbers. They just have to be real. So they could be decimals. They could be fractions. They could be square roots. They could be pi. They just can't be imaginary. That's the only restriction on the coefficients. Okay? And if you add those things together in a string like this, it's called a polynomial. Hugely important function in math and science. We use polynomials for lots of things, but one of the most important things we use them for is we use them to approximate behavior of real-world things. because polynomials are really good at allowing us to, by choosing the coefficients and the powers of x, we can make a polynomial look lots of different ways. And that's good, because then we can make it model real world natural behavior. Okay, we'll get a little bit into that, but more in future years for you. Okay, so let's look at a couple examples of polynomial functions. Now, without knowing it, you've already been using polynomial functions, and you'll see that here in a second. So if we look at the degree of the polynomial and how we describe it, well, if the degree of the polynomial is 0, that's a pretty boring polynomial. It's got one term and it's a constant. So any number actually is, technically, it's a monomial. Poly means many terms, polynomial means many terms, monomial means one term. But that's just like a compressed polynomial. You'd never really tend to think of it that way, because it's not that useful to think of it as a polynomial, but technically it is. A 0-degree polynomial is just a constant, any constant. What do you suppose a first-degree polynomial is? Now think what that would look like. That would look like if the first degree, if n would be 1, right? So how many terms would there be in a first-degree polynomial? 2, right? We'd get something times x to the 1, something times x, plus a constant. John, I see your hand. What do you think that is? Yeah, that's a line, isn't it? mx plus b, we wouldn't call them m and b, we'd call it a sub 1 and a sub 0, but that's a first-degree polynomial. So we say a first-degree polynomial is linear, and it just looks like that. Now we would choose, talking about linear polynomials or linear functions, we would of course choose to call that mx plus b. That's a much more useful way to think of it for us, but really it is just a first-degree polynomial. What's a second-degree polynomial going to be? Quadratic. That's what we just dealt with for a long time, right? That's quadratic. And so that's going to look like, if we put the polynomial in its standard form, it looks like a quadratic function in standard form. Only instead of calling it ax squared plus bx plus c, we just change the coefficients a little bit, right? Same idea though. Same exact properties, etc., right? Third degree we would call it cubic, and then we just add an extra term out front, right? Then the biggest power of x would be 3, so we get some coefficient times x cubed. Fourth degree we'd call it quartic, and after that we don't even really keep, I can't remember what they're called. Why is it quadratic?
Yeah,
well, it's, I don't know. I don't really remember. At some point I'm sure I probably knew that, but I don't know. Yes, sir.
Yeah, because like I thought quadratic meant 4.
Well, quad, a lot of times quad means 4 for us, doesn't it? Yeah, and I'm not sure, I just can't remember why that's called quadratic. I really can't. If I think of it, I'll look it up and see, or you guys can look it up and tell me. And then beyond that, we don't even really keep track. In fact, you don't even have to use these terms. Really, you could call any polynomial, you could call it like a 4th-degree polynomial or a 10th-degree polynomial, and that's fine. Okay, so real quick, just tell me yes or no. Is that a polynomial? Everybody, don't say it out loud, but everybody look at that for a second. Let's see if we can come to some class consensus on this. Okay, we're going to answer some questions here. We want to know, first of all, is it a polynomial? If it is it in standard form?
Yes.
If it is, state its degree, the type, and the leading coefficient. So, is it a polynomial?
No.
I'm hearing a no. How come?
Because the x's are not in the system.
Okay, so yeah, I see what you're saying. Now, it is a polynomial, it's just not written in its standard form. Okay, but as long as it could be rewritten in standard form, then it is a polynomial, right? So to put it in polynomial, or in standard form, we'd have to just turn those terms around a little bit, right? It is a polynomial. There's standard form. I got to put the x to the 4th term first and just go in descending order of power. Okay, what is the degree of the polynomial? 4. Just the biggest power of x. That's it, right? It's a 4th-degree polynomial. So what would the type be then? If we wanted to give that a name, remember what that was called? Quartic. And what's the leading coefficient? -3. What's the constant? -7. Good. Okay. What's the quadratic coefficient? 1/2, yeah, right? That's gonna be the coefficient of x squared, because x squared is what defines that as a quadratic. If it were a quadratic function, it's the x squared term that makes it so, right? What's the linear coefficient? No.
0.
0. There is no x term, right? So the linear coefficient, the coefficient of x is 0. It doesn't even show up, right? Okay, what about same questions for this guy? Is it a polynomial? No. What's weird about that? What disqualifies it?
X is in that power.
Yeah, I have a variable power. That's no good. The powers have to be whole numbers. The exponents do, right? So that's, we can cross him off, okay?
Is this going to be like the assignment?
Well, no, this is just an introduction. Yes or no? Okay, what's the problem with this one? Got a negative power. That's not a whole number, right? Whole numbers have to be greater than or equal to 0. So no go. What about that one? Hunter, what do you think?
Yes.
Yes, it looks weird, but it meets the criteria, doesn't it? The exponents are all whole numbers. The coefficients are all real numbers, no i's, right? So it does work. Is it in standard form? No. To put it in standard form, what would have to be the leading coefficient?
Pi.
Pi, okay. What's the degree? 2? Okay, good. Okay, so we can skip through all this. Okay, here's what I want to show you now. Evaluating polynomial functions. Okay, we all know what it means. Well, I'm assuming we do. Maybe we need to remind ourselves here. What does it mean to evaluate any function? Not solve it. Solve is different. And I know what you probably mean the right thing, but solve is different. Solve always means that we're going to find the value of a variable, right? We're going to algebraically isolate a variable, find the zeros, right? Set equal to 0 and solve. Evaluate is much easier. Evaluate does not involve nearly as much algebra. In fact, it really doesn't involve hardly any algebra at all. Maybe none. What does it mean to evaluate a function?
Simplify.
No? Simplify means we're going to rewrite it in its simplest form. That involves some algebra. That's harder too. Say it again. Exactly. It means we're just going to plug in a value. Value means number in math. We're going to plug in a number for the independent variable, usually x, in this case x, and figure out what the function spits out for that value of x, right? So we're going to plug in an x and find out the value of y, essentially. What does the function give us back? So here we're plugging in the value x equals 3. And direct evaluation just means just plug it in and find out, right? So we would just plug in 3 for x. It's going to give us back an answer, okay? Now, polynomials, that's fine to do, but there's an easier approach to this. And even if this might seem, especially for you guys, it might seem like, well, it's easy enough just to plug the number in. Why mess with something else? So I'm going to tell you right now in advance that this trick I'm going to show you called synthetic substitution it's going to bear fruit, important fruit later. I mean, this is something that you're really going to use a lot. It's a really important concept. And it's just kind of multi-purpose. Really, it's not meant to use to evaluate a function. It's meant to do something else. It's meant to be used to divide polynomials. But sort of a fringe benefit, a side benefit of that is that it does tell us the value of the function. Okay, so we could evaluate directly, but here is a sort of a shortcut, an easier way. And there's a reason, even for evaluation, this is a little bit useful. When you get big powers of x and you're plugging in numbers, can you see that you're going to get very large numbers very quickly, right? And so it is kind of cumbersome to evaluate polynomials because you get such big numbers. Okay, here's how you use what's called synthetic substitution, which really is just synthetic division. Okay, so now you're going to watch this closely. This is a really important pattern that you're going to use a lot in math. We use this a ton even in calculus, for example. So what you do is you write out the polynomial, and by the way, this works only for polynomials. You write out the polynomial in standard form, including all coefficients, even zeros. Okay, and we're just gonna, the nice thing about this is we don't even have to write the variables down. We're just gonna deal with the numbers, just the coefficients. So we bring all those down in a row. Now, if you just see the coefficients of a polynomial without looking up above, just looking at the string of numbers there, how could you tell me what the degree of the polynomial is? Yep, exactly, by counting, by how many numbers are represented. So if there are 1, 2, 3, 4, 5 numbers represented in the coefficient string, what's the degree of the polynomial? It's got to be 4, right? It's always got to be the number of numbers minus 1, because you got to include the constant also, right? So you're starting at 0 and counting up to the nth term, okay? So then all you do is you draw this L-shaped bracket, and you want to leave room for a second row beneath the first, okay? The number that you're substituting into the function goes out front. So in this case, remember we were substituting 3 into the function. And then here's a little game you play. It's really simple. All you do is you start this process going. Now to start the ball rolling, this synthetic process, you take the first coefficient and you drop it straight down to the, and this is technically going to be kind of the answer space. You drop it straight down. Here's the rule. Whenever a number appears below the bracket, you always multiply by x, by the value that's outside, and push that up diagonally into the next column. Okay? And then you add those two numbers and repeat. Add and repeat. Add and repeat until you get to the end, and that's it. Okay? So 3 times 2 is 6. And then add 0 to it. And I want you to remember that with synthetic processes, you always add. Okay? Now this is really for division, and we're going to compare this to long division of polynomials here, not today, but in the future. Long division with polynomials will end up being like long division with numbers, where you subtract, right? When you think about the long division process, and we'll review that, you always, when you get a row, you distribute and then you subtract, right, in long division. Opposite with synthetic division. So we add those up. 0 plus 6 is 6. A number appeared, so what do? Multiply and add, right? 3 times 6 is 18, so 18 goes there. Add, I get 10. New number appears, so I multiply and add. Okay. New number appears, so I multiply and add. And then finally, here's my answer. Now, something they don't do on this PowerPoint that they really should do. There should be a box around your last result, because that's important. This is, later on, we'll think of this as the remainder box, but for now, this is the value of the function. Okay, it tells us the value of the function. So what this says is f of 3 equals 98. Okay? Do you see that that's easier than direct evaluation? With direct evaluation, you have to do exponentiation. You have to take powers of numbers. And if you think about kind of the ladder you climb with arithmetic, addition and subtraction are the lowest, easiest level, then multiplication and division, and then exponentiation, taking things to powers. So this moves us down a step on the ladder and makes the process a little bit easier. Okay? You get that idea, how that works? Let's try a quick example. Okay, I don't want to do that yet. Let's just do a quick example.
Yay!
No, it's not hard. That's not hard stuff, I promise. Let's just do it. There we go. So let's say we want to figure out if f of x equals negative 2x to the 4th plus 3x minus 5. And I want to evaluate this at x equals negative 1. It's a pretty easy one, but we'll just do an easy one for practice. How would we set that up synthetically? Okay, Okay, what would our coefficients be in order then?
-2, 0.
-2, 0, good, because there's no x cubed, so I gotta have a 0 for the x cubed, 0 for the x squareds, 3, -5, good, so we'll make our bracket, we'll put our box around the answer, where the answer will be. What number goes out front? -1. So what do we do?
Bring -2 down.
Good, so we drop the -2 down to start the ball rolling.
3, no, 2.
2.
Sorry.
So what number's down here?
2.
2. Right, everybody see we add? -1 times -2.
2.
Not 5.
6.
Oh, I'm sorry, yeah, 5. What am I saying? You're right. -1 times 5. So what's our answer? Okay, so then we know that this tells us that f of -1 equals -10. How would I write that as an ordered pair, as a point on a graph? What's that mean?
It would be -1.
Yeah, x is -1, right? Y is -10. So it gives us a point on the graph, right?
Wait, how's that?
F of -1 is y.
System though? Like, is that or with the line system and all?
Well, no, this is gonna be some complicated polynomial. This is gonna look strange.
It
Okay,
wouldn't be able to go on a graph.
what do you mean?
It wouldn't be able to go on a graph.
You can graph it on your calculator. We're gonna graph some right now.
Oh.
Yeah, polynomials, and they have a distinct look to them, and you'll see kind of what that is. Let's look at, I don't know if I want to do this next or not. I don't think so. Let's look real quick. Let's just play with some graphs and just kind of explore this a little bit. So, I'm not real good with this new Microsoft Math, but hopefully we'll make this work. So let's see, we want to do graphing. And I'm just going to put in y equals, well, we know what a second degree polynomial looks like. That's quadratic. What's that look like?
AX.
I mean, what's the shape of any quadratic function? Parabola, okay. We know the first degree is just a line, isn't it? Right? Let's just take a quick look at what a third degree polynomial looks like. I want you to see if you can kind of get some idea, and we'll go into more detail with specifics later, but for now, just to get an idea what these things look like. So let's just do like x cubed minus 3x, oops, not liking that. Oh my gosh, what did I do here? I guess I probably, I have to do this. No. I don't get why that's not working. 3. Oh, there, did it. Okay, plus, oh, I didn't say times. 3 times x, let's make that a minus. Squared plus.
Oh, it's because you left the LA equals. It's like when you started doing it and then you hit the space button.
Oh, okay. I got you. That's probably it, yeah. So plus 5 times x minus 10, something like that. Let's make it minus 4. Okay, so let's try that. We want to graph this guy, so what do I do here? Graph. Okay, so there it is. Now let's zoom out so we can kind of see what this thing looks like a little bit more.
It's like one of those weird.
Yeah. Okay, so yeah, it looks a little bit different, doesn't it? It's not a parabola at all. Okay, and we can, by tweaking these numbers, we can make this thing look even. We can make this thing look even different. Let me just make one little quick change on this. What if I go 2 times Okay, and yeah, if I just, what if I make that like a, I wanted to try to give one little tweak to this, but I'm not sure if I'm going to make this work or not. Yeah. What's that? Yeah, I was gonna try to, let's make the Y's zoom in. Okay, so you can kind of get an idea here that this thing can even, I didn't do a very good job of this, but you can kind of see that it can even do this a little bit, right? It can go up and back down. But it's got a little different look to it, doesn't it? Okay. If I added an x to the fourth term in here, it's going to even get a little bit stranger. Okay, so there's the third degree. Hey.
In your spare time, which I know you have hours and hours and hours of spare time.
Oh, yeah.
Will you see why this calculator is goofy? I don't know.
You have a lot of time right now.
Listen. Uh-huh.
It doesn't need to be done right away. It just doesn't work right. Like, something about it doesn't work right.
Huh.
It doesn't do, like, Norioka gave it to, we need to let this kid use because it doesn't work right. So now this kid is never doing stuff right.
Okay.
So, Quinn just said, I bet Oya can fix it.
Yeah,
If it's fixable.
okay, yeah, I'm
We don't
sure
know.
it is. Yeah, I'm sure it is.
But we've been dealing with it for 6 months like this. We're fine.
Gotcha. I can fix it. I'll take a look at it.
Like square.
Okay, so look at this now. Look what that is. I mean, it's like a squared off parabola kind of, right? Okay, so that's an x to the fourth. If I made an x to the fifth, just, oh, this is weird. It's doing this. Huh. Well, that's not what I wanted that to do at all. That's an x to the 12th. I just am kind of weird. I don't like this program. I have a heck of a time getting this thing to work.
Maybe you can go to parentheses.
Okay, there's x to the fourth, right? Turns down. If I zoom out, look at that, it turns back up. W, okay,
Just go back down or?
strange. What do you think is going to happen if I make it negative? Yes, it would. Oh, see, it didn't. It's not what I wanted it to do. Ah, are you kidding me?
Can't you just use your graphing calculator that's on there?
I could. That'd be probably easier, wouldn't it?
It's just gonna keep making.
Nope, got it.
There you go.
So there you go, Hunter. Goes down. Okay, anyway, we can probably leave this thing. If we keep going with this, we are going to notice kind of a trend. And here's the trend that we're going to see.
It's wobbly. Wobbly.
Okay, what we see is that for I don't like this graph. Here's the trend that we see. When we look at polynomials, if we wanted to make like just a rough sketch of some different polynomials. If I make a sketch of a linear polynomial, that's pretty boring. That's a line, right? So there is n equals 1. If I make a representative sketch of n equals 2, that's going to be a parabola. And so that looks like that. If I make a representative sketch of n equals 3, this is just one of the many different ones I could get, but they all share some characteristics. It might look like this. What about n equals 4? Well, n equals 4 might look like this, for example. Do you see a trend? What's the trend?
Well, like the more, the higher you go up, like the more humps they have.
Okay, that's one thing. The higher you go up, the more potential humps the parabola has. We call those minima and maxima. Okay, a minimum would be a valley, a maximum would be a peak. Okay, there's something else going on. What about what we'd call the end behavior of the function? Okay, the end behavior meaning if an ant were to crawl along the graph infinitely far in the negative x direction or the positive x direction, see if you can see a trend there. What's happening? With the line, what do you notice? Compare the line to the parabola, the blue line to the red parabola. What do you see? One thing that's different between the two. John, what do you see?
Well, like on the red one and the purple one, both of those, like both lines that are going in the same direction.
There it is, right? Okay, on the red and the purple graphs, it doesn't matter which direction the ant crawls, the result is always the same. On the red graph, if he goes infinitely far to the left or the right, he ends up going up infinitely far, upward in the positive y direction, right? On the purple graph, when he goes infinitely far to the left or the right, he goes down infinitely far in the negative y direction. But the behavior is the same at either one of the two tails, we'd say, of the function, meaning way out at the ends, right? And obviously there is technically no end, we can go infinitely far, but you get the idea. Okay, contrast that with the blue or the green.
So is it
Opposite. Yeah, it's opposite. Haley, what do you think? Explain that.
Odd ones go both directions.
There it is. There it is. Odd end behavior, if the leading coefficient, if the power of x is odd, then that means that, and we're just talking about one term, aren't we? So if the power of x, if x to an odd power is what we're using, the end behavior is always going to be opposite. If it's an even function, we'd say, if the even power of x, the end behavior is always the same. Okay, now here's the next challenge I've got for you, and this is really pretty cool. Let's look at a polynomial and see if you can make a prediction about what's going to happen with that polynomial. Okay, let's look at something like, how about f of x equals, I can't remember what my colors were, I guess I do. So let's say we do something like this. Let's say we do x to the 4th plus 30x cubed plus 100x squared plus, did I do that wrong? That's supposed to be red, isn't it? $100x squared plus 200x plus whatever you want. Doesn't even matter. Plus, let's just say, I don't know, 400. Okay? What's going to be the end behavior of this function? What do you think? Any ideas? Well, which direction? Left or right? Or both?
On both ways, on both sides, they're gonna go up.
Oh, okay. How come? Why do you think that? You're right. You're right. But why do you, so in other words, you're telling me, which of those colors do you think is going to be the one that's really going to dictate what the ends of the function look like? Why purple? Because it's the leading one. But even though, look at the coefficients get big down here. Shouldn't the 200 with the x make that blue part more powerful than the purple part? The coefficient of x to the fourth is only 1. Haley, what do you think? Say it again. Right.
And because the X.
But in a polynomial, it's just a sum of all these terms. And so when I start looking at this thing, it's just going to look like, let's just make that 0. Obviously, that's not the answer. It's just a sum of all these functions superimposed on each other. That's really all it is. So there's going to be a contribution from each of those terms, right? Which one do you think is going to dominate when we go really far out to the sides on the tails of the function? Now think of the values of x we're talking about. Positive, a trillion. Negative, a trillion. Positive, a googol, 10 to the 100th. Negative, a googol, right? Which of those functions is going to absolutely dwarf all the others? Which of those terms? Hunter, what do you think? Even though it's only got a coefficient of 1? It's got the biggest power though, right? Think how much bigger x to the fourth is than x cubed. X to the fourth is x times bigger than x cubed. That may not be a big deal when x is a small number, but if x is a huge number, like 1,000 trillion, then the purple one is going to be 1,000 trillion times bigger than the next biggest one. You see my point? Now let's look at this in action. Now if we graph, let's just graph this function, and kind of see what happens with this. All right, so 300. Okay, 30. See if we can get this to work. You guys might have to help me out a little bit here because I don't. So what did we say? X to the fourth plus 30 times x to the third plus 100 times x squared plus 200, is that what it was, times x? Okay? Okay, so let's graph that. Okay, so it picks a scale for us, doesn't it? Right, it kind of sets the y window to be pretty high. And at first glance, it kind of looks like, well, I don't know, who knows what that's going to be. It sort of looks like maybe it could be a parabola, but it looks like it's going to be maybe turning back down.
Yeah.
But look what happens when I zoom out. When I zoom out, oh man, it looks like maybe it's cubic, huh? Is the cubic going to win? No way. If I keep going out, look what happens.
No way.
It's guaranteed to turn back. Okay? Now let's just zoom out. Let's only continue to zoom out on y. These are big numbers, but what's happening to that curve? It's starting to look. Let's zoom out in x and y once. Look, it's starting to look like a classic quartic function. That looks, in fact, let's compare that to just plain old x to the fourth. We'll add another equation in a different color that's just x to the fourth. Okay, now how do I make that a different color? Come on. Okay, so blue and green? Oh man, I didn't. Okay, I got to zoom out again. I want you to watch how these things diverge. Look at the green one. Okay, the green one is just on the x-axis right there, right? So we'll go zoom out, zoom out, zoom out. The green one, look, that's x to the fourth. The blue one doesn't look anything like that. Or does it? Isn't that cool? We're getting pretty big numbers. We're out there into the millions now. But eventually, you almost can't even tell that there are those other terms there. If I go out far enough, I won't be able to. mean, look at that. You can't even, at that point, you can't even tell,
Agreed.
right? So what's the moral of that story? Well, the moral of the story
Is it a big, if it's,
Is-
zoom down on that?
Yeah, now to me, that's pretty cool. If you go really far out in either direction, so we're picking really, really big positive or negative values of x, the only one that matters at all is this one. The rest of those don't matter a bit. They're just a blip on the radar, and eventually, as x approaches infinity or negative infinity, they don't matter at all. They make zero contribution. It's only the leading term that matters at all, right? How would we write that? Now, this is going to look a little bizarre, but I want you to see this because this is how you're going to talk about it in pre-calculus and calculus. What do you suppose this means if I say the limit of f of x as x approaches infinity? What am I really saying? What do you think I'm saying there?
Limit of large, or
We want to know with a limit, and we'll go into much, much more detail with this in calculus, but a limit is really asking us, what are we approaching? What is if x goes towards a certain number, or in this case, it goes out infinitely far to the right, what is the function doing, right? The answer is, in this case, positive infinity, okay? We'll wrap this up real quickly because we're about done, and then I'll put the new assignment up. You guys can have a lab day tomorrow.